All right, so we are on chapter 8, section 2. And so we're going to talk about how solutions formed. We know what solutions are now. Now we have to know how they're formed. So you kind of have to remember those interactions that we did in the last chapter. So you have to remember that polar covalent compounds and ionic compounds are going to be able to interact with water either through dipole-dipole interactions, hydrogen bonding interactions, or ion dipole interactions. Either any of the three are going to be relatively strong attractive forces that exist between the solute and the solvent. So the solute are those compounds that you're dissolving in the water, which is the solvent. Now, nonpolar covalent compounds are not soluble, right? They're nonpolar, so they can't participate in dipole-dipole interactions. They can't participate in hydrogen bonding. They can't participate in ion dipole interactions, none of that. So they're not soluble in water. So you have to keep track of being able to look at molecules and know what's polar and what can dissolve and can't dissolve. Amphipathic molecules, on the other hand, those are the ones that have one side that's positive and one side that's negative. So like those fatty acids, where we had a polar head group and then a nonpolar, really long carbon chain, right? Those can interact with water on the polar part, on the negative part, but these molecules usually don't form solutions because they have that big long chain that's nonpolar, right? So they can get distributed, but they don't actually dissolve. In order to dissolve, those solvent particles have to, the water particles, usually water, will surround the solute, right? And so they'll interact through those attractive forces, but it has to go all the way around the molecule, right? And so that process is called solvation or hydration, if we're talking in specific about a aqueous solution. So there are a couple of different factors that can affect solubility and whether or not your solution is saturated. You might have heard before a saturated solution. What does that mean? Well, it depends on how much of your compound you put into your solvent, right? So if you had a glass of water and you decided to put as much sugar as you could into it, what would happen? Well, in the beginning, you'd start out with a tablespoon and you put it in and you mix it and everything would go into solution. So that would be an unsaturated solution because you could take another tablespoon and put it in and stir it up and it would still dissolve. So at 2 tablespoons inside of your cup of water, it's going to dissolve, right? But now, what if you add by like the cupful, right? If you have a cup of water and then you put a whole cup of sugar in, it's probably not going to quite all dissolve, right? You're going to end up with some solid sugar particles that are not going to dissolve. And so if you get to the point where you have a solution and you're adding a little bit of sugar, a little bit of sugar, a little bit of sugar, and you get to that maximum amount that can possibly dissolve in the solution, that is saturated. You add more and it becomes to the point where not everything's going to go into solution. It's still going to have some solids. So if you add more solute to your saturated solution, the additional solute will remain undissolved. It'll remain a solid. So once you get to that point, you got a little bit of solid inside of your solution, there's an equilibrium that exists between the dissolved state and the undissolved state. And so you have molecules that are always kind of cycling through that. They never always stay dissolved or always stay undissolved. You just kind of have molecules cycling through that in that equilibrium. And so if you look at the rate of the dissolving solute and the rate of the dissolved solute turning back into a solid or recrystallizing, you can represent that equation with a double arrow, or we call that an equilibrium arrow. And so if you look at that, here's the example, right? You have your undissolved solute and here's your double arrow right here. This is your double arrow to the dissolved solute. And so that's what they're showing you here. So you have these glass of water and you're putting sugar in and you're putting sugar in. And if it's unsaturated, you could still put some more sugar in. But once you get to that saturated solution, you've got some solid particles down here that are going to go into this cycle of, well, a particle is going to dissolve, but at the same time that one particle dissolves, one particle is going to recrystallize. And so they'll constantly go through this cycle over and over again. And this is really important inside of our bodies because the concentrations of substances inside of the liquids of our body have to be within certain limits, have to be. Otherwise, you get disorders. And gout and kidney stones are two disorders that come from a difference in the number of substances or number of moles of substances that are dissolved inside of a solution. So in both gout and kidney stones, whatever the compound is, it's exceeding the solubility limits. And so we have some of those solid particles that are in what should be pure liquid, and it causes problems. So in the case of gout, the compound's uric acid. And so your kidneys are supposed to filter out uric acid and you're supposed to urinate it out. But a lot of times that doesn't happen in these patients. And so you end up having a buildup of uric acid in your bodily fluids. And so because so much of it builds up, it actually crystallizes and becomes insoluble. And the crystals are needle-like. I mean, they really just look like needles. And they form inside of cartilage, inside of tendons, at all of their joints. And it causes swelling and pain. And it's really a painful disorder. Kidney stones are very similar, right? They can contain the same substance. They could contain uric acid. They could contain calcium phosphate or calcium oxalate. And it doesn't matter which one it is, but they could either form in the urinary tract, in the kidneys, in the ureter, in the bladder. And you got to think that all of those structures are designed for liquid only. And so once you start having solid things inside of the urinary tract, anywhere inside of the urinary tract, it's going to cause some serious pain. And so this is what happens when those compounds basically crystallize out. So you can treat both gout and kidney stones with changes in diet and with drug therapies. So the other thing that controls the solubility of substances is temperature. So if you have a solid and you're trying to put it into a liquid, if you increase the temperature, you're going to get more solid to go into that liquid. And this is why if you know someone who makes their own tea, like iced tea, like old school, from a tea bag tea, what they do is they heat the water, they put the tea bags in, and while the water is still hot, they're gonna put the sugar in so that more of it dissolves, right? Otherwise you end up in it like gritty. If you put it in while the water's cold, it ends up kind of gritty, and that's because not everything has gone into solution. So you can manipulate solubility just with temperature. Now gases are a little bit different. Gases, you got to think about it. When you increase the temperature of something, that's going to make those molecules move faster. So you have a greater percentage of molecules that are going to escape the liquid form and turn into the gaseous form. And so when you increase the temperature of a gas that's dissolved in water, it's actually going to decrease the solubility. And this is something that you can see in a can of Coke. Right? If you leave your can on the counter, you pop the top, you leave the can on the counter, you come back, it doesn't take long and it's flat. But if you pop the top and stick it in the fridge, you can come back the next day and it's not flat yet. Yes, some of the gases come out, but it's not all the way flat. And so that's just your representation that temperature will control solubility of gases. So this relationship between solubility and gases and pressure. Oh, I didn't say that. Sorry, y'all. The other thing that controls solubility is pressure. So pressure, this is, again, you can relate this to a can of Coke, right? If you don't pop the top, right, all of that carbonation is soluble inside of the liquid. Right? So that all of the gas is inside there. But when you pop the top, you hear the psh, right? So those are those gas molecules that were in the liquid that are now out into the gaseous form and they are escaping from the can, right? And so the higher pressure you have, more gas can be dissolved inside of the liquid. The lower pressure, the more the gas just escapes. And so this is Henry's law, telling us that the solubility of a gas is related to the pressure that the gas is under. So This is really important not only for drinking your soda, but it's really important for breathing. So when we breathe, right, the pressure that's exerted by carbon dioxide, so your cells undergo metabolism and they produce waste in the form of carbon dioxide. So carbon dioxide will be in the tissues and it'll get picked up by the bloodstream, right? And so you have blood that has carbon dioxide that's coming around. And then you also take a big deep breath in, and that big deep breath in has a low amount of carbon dioxide in that air. So it's low pressure. And so what's going to actually happen is that the gas that's under high pressure that has lots of CO2 in it will actually move to the lungs. And so if you think about that, exchange occurs in the opposite direction as well, because when you breathe in, you have a high pressure of O2 inside of the air that you breathe. But inside of your bloodstream, you don't have so much O2 because your cells have picked it up and they've metabolized it and they've turned it into carbon dioxide. So now you have high pressure in your lungs of O2. And so that O2 is going to then move into the bloodstream. So at the same time you have O2 moving from your lungs to your blood, you have CO2, carbon dioxide, moving from your bloodstream to your lungs. And so then you've basically oxygenated your blood and gotten rid of the carbon dioxide. And then that blood will take a trip and go to all your tissues and do the same thing, drop off the O2, pick up CO2, and make the block again. And it'll happen over and over and over again. And so this is just showing you the number-wise what's happening, right? Because as you inhale, if you look at the amount of CO2, right? If you look at the amount of CO2, we only have 0.3 millimeters of mercury. Well, look in the bloodstream. No, they didn't show you in the bloodstream. So they want you to look at CO2 on this one. O2, sorry. Okay, so here, when you inhale, you have a high concentration of O2, 160 millimeters mercury. They're showing you in the bloodstream, you have a lower concentration. So you only have 100 millimeters mercury of O2. So you have more oxygen in your lungs than you do in your bloodstream. So what's going to happen is your oxygen, O2, goes to the blood. Okay. If you look in the bloodstream, what you're going to see is your CO2 is 40 millimeters mercury, where here in the atmosphere, in the air that you just breathed in, it's only 0.3. So what's going to happen? Well, my CO2 is going to go from blood to air in the lungs, to exhale. And then you get rid of it. And that's how we clear CO2 from our bodies. All right, so let's go do a few problems. Okay, so we're on our in-class problems. So do the following represent a saturated solution? A pinch of salt thrown into a pot of boiling water. That's a really high temperature and a really small amount of salt. So that is not a saturated, no, because remember, a saturated solution contains the maximum amount of solute particles, CLES particles, the solvent can hold. So there's kind of your definition of that. All right, a layer of sugar forming at the bottom of a glass of tea as ice is added. Ooh, we changed our temperature, and because we dropped our temperature, things started precipitating out. So now this becomes a saturated solution. So yes, it is saturated. We gotta go down. All right, fill in the blank statements with the words increase, decrease, or stay the same. So my suggestion to you is before you start reading this and start like getting a little bit confused, maybe write yourself a few notes, right? So if you have a liquid and you increase temperature, what happens? You increase solubility. And that's not quite true for a gas, right? A gas is a little bit different. What happens in a gas? In a gas, I guess I should move this over here. In a gas, as we increase temperature, what's going to happen? We're actually going to decrease our solubility. So gas inside of a liquid. This is a solid inside a liquid, right? And so what happens if you increase temperature? What are you actually doing? You're decreasing the solubility inside of the gas. And so you're losing gaseous particles into the air, right? Okay, so 8.7, let's see. If the temperature of the solution increases, the solubility of most solid solutes, okay, so we have a solid solute, will do what? So our solubility should go up, it should increase. This is saying if you have solid solute sugar, right? If we increase the solution, the temperature of the solution, so this is water, right? If we have water and we increase the temperature, we can get more sugar to go into solution. If the temperature of a solution increases, the solubility of a gaseous solute will do what? It will actually do the opposite. It will decrease. It will decrease. That's why if you leave a soda can like in your car, right, and it gets really hot, and you open it while it's really hot, it's gonna like really, it's gonna really make kind of a mess. And so that's just telling you that you have more gaseous particles, and so that increase the pressure, right? So if the pressure above a solution increases, what happens to the solubility of our gas? Well, if we increase the pressure, then we're gonna make more of those gas particles go into that solution. And so you're gonna increase it. So remember, if you actually increase the temperature enough, right? If you have a can that's under pressure and you increase the temperature enough, I know of people who have had cans of soda explode in their car. Can you imagine how much of a mess that is? All right, explain what is happening in the following situations in terms of solubility. An open bottle of soda goes flat more slowly when recapped and stored in the refrigerator. So what did we do? If we put it in the refrigerator, we decreased our temperature. So you decrease temperature. What happens when you decrease temperature? You increase solubility of what, right? You have to be careful of this because you just can't say increase solubility because it's opposite for solids and gases. So it increases the solubility of a gas in the soda, right? And then the other thing you have to talk about is it was recapped, right? So if you cap the bottle, so a capped bottle, right, keeps the high pressure, right, which will increase solubility, solubility of the gas, okay? All right, a bottle of fizzy water keeps its fizz longer if the lid is screwed on tightly. Okay, well we just said it. We just said it right here. It's the same thing. A capped bottle keeps the high pressure, so you increase the solubility of your gas. All right, less sugar dissolves in cold iced tea than hot iced tea. So here, our solubility is different, right? So here, our solubility of our sugar, and really this is true for most solids, right? So our solubility of our sugar decreases as the temperature decreases, right? So lower temperature means less sugar dissolves. Okay. All right, let's see. Where would you expect a freshly poured glass of champagne to hold its bubbles longer? I like this question. I like this question a lot. In a mountain resort at an elevation of 5,000 feet or on a beach at sea level, does it really matter? As long as we get to go on a mountain resort or go to a beach and drink champagne, that sounds perfect. All right, so assume that the champagne is at the same temperature. So that's kind of an important assumption to make. So what you have to kind of remember about this is that there's an elevation difference, right? A mountain resort, we're going up really, really high, or we're going to stay really, really low on the beach. And so as you increase your elevation, as you increase your elevation, the air gets, have you heard this? The air gets thinner. right? What does that mean? That means you have fewer gaseous particles, so that's a decrease in pressure. So if you go up in elevation, you have a decrease in air pressure. I guess I shouldn't just put P, I should put air pressure. Okay, so so what do you think would happen? Well, I want to drink, well, it doesn't really matter, but if you want the most amount of bubbles inside of your champagne, what you need to do is you need to drink it at sea level. You need to drink it at sea level because our atmospheric pressure at sea level is lower. Because you have lower pressure, so more bubbles. Oh, I'm sorry, you have higher pressure. Blah, blah, blah. You have higher pressure, right? At high elevation, you have low pressure. So at sea level, this is low elevation. That's what I was mixing up. You have low elevation, so then you have high pressure. So more bubbles stay in the champagne, right? I'm too busy thinking about enjoying champagne on a beach. All right, that's it. That was a good one to end on. All right, y'all have a great day.